Hi, I'm Ray Yellow, and today I'll be talking about projectile motion in 1D and 2D for Physics 2A students. Well, we just talked about the kinematics equations last video, and now what we're going to do is try to use them. We're going to put them in action, first with a one-dimensional problem. And so imagine I am throwing something into the air, and we don't have to worry about air resistance. We're going to have a constant acceleration due to gravity. So we want to find out how high is whatever I'm throwing going to go. So we're going to call this y. That'll be how high it goes, the final height. So we're just going to pull out two kinematics equations, and we're going to take advantage of a few things to make it easier on ourselves. So we know that v equals a times t plus v naught. So at the very top of this throw, we know that for an instant, the velocity has to be 0 at the very top of its arc. Before it comes back down, the velocity has to be 0 at some point. It's going to be positive, 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 and then it's going to be decreasingly positive, and then it's going to become negative, and then increasingly negative. So there's a symmetry to its path. And so we know at the very top of its arc, we know v has to be 0. So we'll say from this guy that the velocity at the top equals 0 equals a times t plus v naught. Okay? Now a is going to be going down this way. That's equal to gravity. That's going to be negative. But v naught is going to be the initial velocity that we launch it with, and it's going to be going in the upward direction, so it'll be positive. So when I have a 0 equals negative g times t plus v naught, well, I know that g of t, or g times t equals v naught, and the time it takes to get to the top of the path is going to be v naught over g. So if this, a lot of times Eichmeier will use 10 meters per second as g, because it's pretty close to 9.8. So we know that if the initial velocity here were 10 meters per second, we'd have 10 meters per second over 10 meters per second, which would just be equal to 1 second. In that case, it would take 1 second to get to the top of its arc. And so now we solve for t. We can put that in here. That equation. I'll say, well, we don't have a y naught. The y naught, in this case, will just be the ground, which is 0. So this is a really good setup if you want to find how high something is going to go. When you start getting into more complex projectiles that are going in 2 dimensions, they might be launched up toward the top of something, or off of a building, or crossing a field. What you're going to want to do first is find out what's happening in the y dimension. So 1D stuff is a really good way to get started on projectile motion, and finding the peak of the path, or the time it takes to get to the top, is really an important skill to get, because it's going to come in handy many times over in this class. So here's something to think about. If it takes 1 second to get to the top of the path, then how long does it take till it comes back to Earth, right? Well, of course, by symmetry, it's just going to be 2 seconds, because this time up has to equal the time down. And we can show that as well. So if we were to drop this ball, I'm going to do this again, and drop this ball from the same height. So we will say here that velocity equals at plus v naught. That's just from page 23 of your kinematics equations. And if we drop it, v naught is 0. Give it no push. And in this case, we'll make down the positive direction because it's the direction of movement. It just makes our math a lot easier. And solve for t again. And so t equals the final velocity at the bottom over a. And so as you can see, this is the exact same as here, because we know that the velocity at the bottom here has to be equal to the v naught from throwing it up there. And we know that a is equal to g, so this is the exact same problem in reverse. In fact, when you do more projectile problems, you'll find that sometimes solving them in reverse is a little easier than solving them forward. You can take advantage of certain symmetries to make your problem a lot easier. Some of the problems will be really complex, like if you were to throw, the juggler throws a ball in the air, and it stays in the air for 1 second. How high does he have to throw it to make it stay in the air for 2 seconds? You can take advantage of the symmetries of this to make that problem a lot easier. Instead of following the entire arc, just look at dropping it, and it should make the problem a lot easier on yourself. So one of the problems that comes up in WebAssigns and quizzes and exams over and over again is a 2D projectile. Usually it's something that's launched either from the ground or from off of a table. So if I were to push this pen off the table with a certain velocity, I want to see how far it's going to go. So this is the simplest version of this problem, and it's a good one to get a really good handle on. So first what we're going to do is we're going to find how long this ball is in the air, okay? And we're going to notice a few things. First, the Vy naught equals 0. We assume that we push this ball completely horizontally, so that means nothing's happening in the y at all, which makes our work makes it just really easy. And we also want to keep in mind that anything happening in the x direction has 0 acceleration. Okay? So 0 acceleration means a constant velocity. If I throw this pen across the room, I know that there is an acceleration that's going to drive this pen back down to make it follow a parabolic arc. But I also know that nothing's happening in the x direction in an ideal form except for air resistance, which we're not going to account because it's going to be negligible. So that's why I can say that x equals Vx naught times time plus x naught, because it has no acceleration term. And we're going to write our y equation as 1/2 at squared plus Vy naught plus y naught. You can change out these variables as you like, whether they're y or x or whatever, just to make your problem easier. Whatever kinematics equations you can use in the x, you can use in the y, but you just got to make sure that an x direction is not going to have an acceleration component. So you're going to want to tweak that just a little bit. So here we go. The first thing that I would do from here is solve for the time. So we know that y naught is going to be given. We'll call this y naught. And so from there we can say that this y at the bottom is equal to 0. So from there we have Vy naught is equal to 0. That term goes to 0. y at the very bottom is going to be 0 as well. And since the direction of travel is going to be in the same direction as the acceleration, I'm just going to make both positive. So here we go. We'll say that, 0, I'll write this off to the side. From this equation, we'll say 0 equals 1/2 times negative 9.81 meters per second squared times t squared plus y naught. Okay? So y naught equals 1/2 g t squared. We can say that t is the square root of 2 y naught over g. That's the time that it is in flight. And the second step is really easy. We just have an x equation to deal with to find out how far it's gone. If we set this point here to be 0 in the x direction, we can say that x naught equals 0. Okay? And we have, we're assuming that they give us an initial velocity. Most of these do, but some of them might be in reverse. We might be given a distance traveled, a distance traveled over here, and then solve for an initial velocity, but it's all the same. It's just algebra, nothing to fear. So the x would just be the vx naught times t. Vx naught times t. Just like that. And so you just plug and chug. Later on we'll get into more complex projectile motion problems, but these ones should keep you busy at least for the first few weeks. I hope that was helpful.